Okay, so um, we are going to talk about our last topic today. So it's flow matching, which is a more popular version of diffusion models. And also we'll talk a little bit about DIT, so which again is the most popular version of architecture for diffusion-like models. So yeah, so and this basically concludes all the lectures. So hopefully this covers everything which is common in the generative AI. So the most frequently used models and some methods. So okay, so let's look at this. Um, So outline. Yeah, essentially we will talk about why we look at flow matching, why that becomes popular, um, and what's the problem of a diffusion model, right? So and then what it resolves with the flow matching. So I mean, so the description we will give is slightly different than what's actually. If you look at the flow matching pair, it doesn't say much about the way we do. I think if you look at the way we do, then you probably have a better ideas why we want to do that this way. And it comes with some problems with the diffusion model, which we already encountered. We just didn't spell that out explicitly. The problem is actually, if you look at what the diffusion model, right? When we start with the diffusion, we say it's approximate light Gaussian. If you recall, the t goes to infinity large enough, right? But it never goes to infinity t, right? So you cannot be exactly like a Gaussian. So, but then you replace that by Gaussian. So that's the part which actually doesn't happen with flow matching. Flow matching comes out with exactly Gaussian, and the reason is we will see that in the mathematical derivation. So why that's possible. So yeah, so we start with DDIM. Recall DDIM has a deterministic version, which, as I mentioned, it's more popular for the case that you don't need a lot of examples. So in the more standard or more practical ways of applying that, flow matching and DDIM, both using deterministic, and that's the way it's been done. So we will start with that and then see what's the problem of that and modify. I think another thing is the last lecture we talked about the UNet. That's very natural for a diffusion model because it's a modifier of CNN, right? There's a convolution or rest block, whatever, right? So with a downsampling, upsampling. So from that perspective, you can think about CNN is for classification, and UNet is for generation. Basically, the dimension is the same of input and output when you predict the noise. Diffusion is it's more direct. If you recall what we did last time, the UNet for the stable diffusion, right? So that implementation, which is based on the latent diffusion model, they do have some transformer-like components, cross-attention, self-attention, whatever, right? So in that, but it's not a pure transform. Diffusion transform actually is even simpler than UNet. From that regard, it's just to say you just use a standard transform. So that's basically what it is about. And it becomes popular. Most implementation now try to shifting from UNet to transformer architecture, even for stable diffusion 3. These have many advantages, right? The first advantage I would say is certainly there's a more capacity when you have a larger one. So this is the property of a transformer. A single transformer is this architecture that's more scalable than a lot of other architectures. So this is, you can say it's a miracle, you can say so whatever it is, but basically this is observed. The larger, the better. When you do UNet, when you do the other things, they up to some limits. Part of that is this kind of inductive bias. Part of that is downsampling, upsampling. You lose some information and so on. So when you have a large amount of model, it may not be the right approach. So let me put this down. Yeah. So basically, this is another advantage. Actually, it's a more interesting is yeah, a lot of modern designs. There are mixing about for example, this transformer or this image generation with autoregressive models, both in terms of image autoregressive or just image and text mixture. And certainly you have a unified structure, it's much easier. So basically, this is the most up-to-date architecture, all unified under a transformer. So this is why it's important. Anyway, so these are the two things we will talk about. Let's starting with the first one, the flow matching, right? So we will recall from diffusion model with DDIM. DDIM, again, there's a deterministic version, which is what we talk about. In diffusion, we start with observed data sample. We forget about the conditioning for now, right? Conditioning can always be added, just like we see that from last lecture. Then define a noisy conditional. Basically, this one is coming from Y0, which is original image, to your YT, which is noisy image at time t. This is a formula. So this is the same in the DDIM and the DDPM. DDPM is the earlier one. It's the first one to make diffusion model works. It has stochastic sampling. DDIM, if you recall, the same forward, the same training process. For the reverse, it gives a smarter reverse so that it can do deterministic reverse. So that it's that. So this is the equivalence, right? So how do you generate YT, the T's level of your denoising, and then that. Train a noisy network. So you predict the noise. Here is actually what is the difference of flow matching versus diffusion model is what to predict. We will see later. So, but you start with that. So this is for the diffusion model paper. Inference. This is a deterministic inference. So basically, you just predict the y equals y0, and then you do update. So this is a predict the y0, right? It's from your noisy network. And then once you have that, you have then you have this guy, right? So this is predict y0, and you have this guy. So basically, this is the inference. That's basically what it is. You could generalize it with arbitrary AT and BT. Yeah, we will work with arbitrary AT BT because the flow matching usually works with a simpler one. We will soon see which is people favors about that. It's just a linear flow, but we will apply to that with the DDIM to see what happens. Yeah, so basically, in diffusion model, you have this, right? This is actually your A and B, so that's fixed. But in the flow matching, actually, AT and BT are different. AT will be 1 minus T, BT will be T. So basically, it's a linear interpretation. We will come back to that later. And then you just form a diffusion, right? You can do a similar things for the general A and B. For the DDIM, essentially it becomes like this. So this is a formula if you have derived the DDIM for general. We will not go over that, but this is something pretty straightforward if you look at what you will see before, right? Basically, it's a kind of, you go to, essentially it's like a predict Y0 from YT, right? And this is a prediction. So by using this formula, right, Y0 from YT, and then once you have a Y0 to YT, you plug that in, Y0, to get Y, say T minus 1 or whatever. But a T doesn't have to be T minus 1. It's a TS because in the flow matching, it's a T becomes 0 and 1, right? So it's not integer. It's a continuous T. So that's why we make it a little bit more general to say for any S smaller than T, you do this. This is just essentially it's basically say the following. From YT, I can predict Y0. From Y0, and plug that in to have a YS, which is S is a little bit smaller than T. And then you gradually denoising. You do not, this one is not good estimate if just one step. But this is, if you plug that in to do a very small step size, then it's a good estimate. Basically, each time you get this. This works, basically. This one is the DDIM formula for arbitrary AT and BT. So you can do the math, the same math applied to, it doesn't require AT and DT to be exactly like this. It can be more general. So basically that's the point, okay? Let's look at this formula to see what's the problem it has. If you say, okay, I want to apply this formula, right? And then you will immediately see a problem. And this is where the flow matching fixes. Actually, it works with all has a problem, but let's just look at this one. This one is favored in the flow matching literature, and this is the one which people now use most frequently. If you look at what people do, they mostly doing flow matching instead of a diffusion model using this particular interpolation, right? T is continuous from 0 to 1. So basically, you divide this interval to be, let's say, 10 steps or 20 steps. 10 steps is 0, 0.1, 0.2, up to 1, right? Or 100 steps or whatever. But basically, you subdivide this interval, which will be the t will be within that interval. Then you have this guy. So this is the formula. So when t equals 0, it's y0, right? T equals 0, this noise is, there's no noise. T equals 1, there's no y0, it's only noise, right? So essentially, it's an interpretation between your original image and the noise. On one hand, it's original image. On the other hand, it's a noise. It's if I pick t equals 1, you exactly get the noise. It's a little bit different than the diffusion model. A diffusion model, when you are thinking about a large T, right? In the T is large, it's approximate noise because T, if you look at this guy, maybe I'll just go to this guy. This guy, you never get this to be 0, actually, in diffusion. If you have a 0 here, then this one becomes noise, right? But then you encounter a problem which is exactly the same problem what we do. That's why, in the DDIM, this guy never goes to 0, okay? So if you recall in our lecture before, we say large T. We don't say the, alpha is 0. So y is the same problem. We'll immediately see what happens with y0, okay? So here is this guy. This is your prediction of y0 from your denoising, right? So this is from the previous lecture, previous frame, yeah. And then that basically this is exactly you multiply that together. So this is your S from y0 plus some noise. This is a formula from here with y0 substituted by your denoising network. So become that. Now, if you look at that, what do you see, right? What happens? What exactly happens is this guy is not well defined when t equals 1. The same issue will come if you use original diffusion model. But because we are looking at the flow matching, we were specifically looking at this. We could look at the more general T, but this one is so at for example T equals 1, this guy, right, is a y minus epsilon, is a finite. This is a noise, right? This is a y, and then basically, this is the problem is you divide by infinity, divide by 0. So you T equals 1, this divided by. So this makes it very unstable if you use a diffusion model. If you really use this guy diffusion model, try to work on this, then the point is because of this guy, right? Divided by it's and this is why in the original diffusion model you never get alpha equals 0. You start with alpha. The T is finite. Alpha is close to 0, but not exact 0, because otherwise you get a division by 0 problem. This division by 0 problem is fixed by flow matching, so that flow matching has a much simpler ways of doing that. How do you do that? It's actually just algebra. So we will look at that, the algebra. Yeah, this is not well defined, basically. Yeah. Okay, so you cannot directly using diffusion model nicely without numerical problems. Just plug this in. So that's that's one thing. Flow matching does that slightly different way. Then it's completely resolve this problem. You just have a different, instead of predicting noise, predicting the flow, so-called, okay? You look at this guy, right? So this is the same now. Instead of predicting epsilon minus y0. So this is your so-called velocity or flow target, okay? So what is the benefit of that? We will soon see, right? Epsilon minus y0 is, I mean, if you think about that, you could, because when we predict epsilon, right, we use that to get y0. So there's a relationship of y, epsilon and y0 based on this formula, right? This one formula say this epsilon is y0. But there is a good benefit about epsilon minus y0. So epsilon minus y0, you will see what eventually happens. It actually has some cancellation effect. So this one actually, if you think about these two objectives, flow matching and the diffusion model, they has to be related. It has to be more or less equivalent in some sense. Because one is just predicting this guy. The other predicting instead of this guy, this one minus y0. But there's a formula here, right? So they are related. So you can say, okay, minus y0 here, then you again have some formula. So yeah, but it solves the stability problem. So this is one. By the way, this is another way. This people writing, right? So they write a slightly more different way. But if you look at if you implement the algorithm, what actually happened is exactly what I mentioned: the stability at y equals 1. So you do this, right? If you change the target, using the same relation is basically equivalent. This is exactly equivalent relationship. Velocity, right? And this guy has. So you can say, oh, it's nothing because it just change of network, right? It just you really even know the relation, right? But in reality, it's not quite as a change network. Is you are predicting something which is finite, so that you make sure you do not have any numerical issues because of this 1 minus t issue, okay? So anyway, so this is what it is, right? So basically, this is the formula we see before, and then you can rewrite this guy, and so that there's a relationship. Now you can use this relationship. You can plug in the IM formula, and then you basically get back your flow matching formula. And what it is that? It's actually very simple once you get that. So this is the advantage of this. Can be rewritten V without any. Soon we will see that next time. So why we want to do that? the main problem is, so if you, instead of predict the epsilon, as in the diffusion model, or as in the PM, DDIM, you predict a V, just a change of a target. So it's one line change of code. It's a very simple change of code. Once you have that, the inference becomes significantly simplified without this 1 minus 1 minus t. Okay, we will soon see that. But I hope the logic is clear. If you have questions, let me know. But otherwise, we will go. But the logic is getting rid of this. This. So here is a formula. You just plug this guy in. This is coming from this guy, right? Epsilon is this guy. So basically, epsilon net is this guy. And then you have recall this one is from previous, right? And recall this guy is this guy, and then you substitute this, and basically what it is, right? So if it's just simple algebra. So I don't want to go the details about algebra. You can do that algebra yourself, and simplify this guy. You get this formula. So this is basically the formula you get with flow matching, just by changing your prediction target. Prediction epsilon to prediction of velocity, velocity epsilon minus y0. So essentially, it's just velocity times this guy, and there's no 1 divided by 1 over t, right? If you think about epsilon is finite and y0 is finite, right? So essentially, epsilon minus 1/9 is finite, so you can easily learn some reasonable bounded function. And this one can never be infinity goes to, right? So unlike this flow, so nowhere you see infinity. So this is a key. In the diffusion model, you see some infinity, which you have to deal with carefully. Otherwise, you will have a problem, because when you do the machine learning, right? They don't know the scaling, right? So they could just screw up with some precision issue. So here is what is the formula. And then you can use this formula using that particular linear scheduling, which is most popular for flow matching. It could use other scheduling, but the linear scheduling, because of this, is so simple. And it works well in practice, so that it eventually becomes more dominant. Most people looking at this particular linear formula of generating YT from y0, and when they do the reverse generation, they start with Gaussian. Now you can start with Gaussian with t equals 1, right? This is y1 is truly Gaussian, so there's no approximation. Unlike PM, DDIM, you start with approximate Gaussian, you just replace by true Gaussian, right? And this one is so-called, you can go that to be infinitesimally small. Then this becomes so-called ODE, ordinary differential equation. For DDIM, you can also have ODE. For DDPM, so-called SDE, stochastic differential equation. Differential equation, but this one goes, and then this one, this particular formula corresponds to so-called Euler methods. That Euler and the DDIM is kind of the same type of methods, but sometimes people use some others. We will mention that later on. But this is a formula which comes directly from the DDIM formula, just replacing this target by using epsilon to epsilon minus y0 and some algebra to get that. I hope this makes it clear why you are preferring flow matching. The key is reverse is so simple, there's no infinity. Therefore, in the forward, the only thing is your learning target is changed to accommodate this, okay? Otherwise, it's pretty much the same as the diffusion model. Actually, they are equivalent. If you think about that, it's more or less just equivalent methods. It's an equivalent method for DDIM with a different target prediction. So here is the algorithm, right? So you can think about this simple interpreter with these people like. And the reason I like this is, it's just linear, but also it works well in practice. Also, the reverse is very simple. The target is this guy. And you use this regression, right? So if you use a diffusion model, the regression target is epsilon. Now this regression target, your network's target, is epsilon minus y0. So this is your loss function. MSE of with this target, we generate from y0, epsilon, and t. Okay. And the algorithm is you are doing this, sampling from this guy, and the sampling t now uniform from 0 to 1. And you are building this guy, right? And then regress up to this one using this loss function. So that's the that's basically what it is. And you have this code. The code is pretty simple, right? It's very similar to the diffusion model code. You're starting with noise. This one is a random generation from a t, right? T is 0 to 1. And yt is 1 minus c times y0 and times this one. This is a linear scheduling. And the target is epsilon minus y0, right? Diffusion is epsilon. And then you have a model predict minus, this is a mean squared error. And then you have optimizer. So this is a training loop you would write for flow matching. It's a very simple training loop, just a few lines of code. And it's again, it's a regression target, similar to diffusion model, so it's pretty stable. It's easy to learn because we know how to learn regression, right? So yeah, so basically that's all it is, and it's a different target and avoids the infinite blow up. So this is the key why, and the inference is simple. Diffusion model, if you are not implemented correctly, if you modify the scheduling, for example, if you say, okay, I want to use a diffusion model with this scheduling, then you have to tune quite a bit. It's not as simple because of this blowing up issue. You could probably magically avoid that by smartly manipulating how you sample t and so on. But this is kind of painful. You can try. I mean, if you are interested to say, oh, I don't believe I should do that. I think because they are mathematically equivalent, right? I just try to use epsilon and try and use the DDIM formula to see how I can come out. And you will immediately see there are some numerical issues, unless you do that very, very smartly. But flow matching, you don't need to worry about anything. The thing doesn't exist, the infinite thing. Yeah. So this is a key. Stability is the key about flow matching, make it popular. Inference algorithm. As I mentioned, we have a continuous version, so-called ODE, right? So for the flow matching, the ODE is you are having infinitesimally small interval. For example, we start with y is t equals 1 up to t equals 0.999, right? And 0.998 and so on. Very small continuous time. So this one is, and this is a formula. But for people doesn't know what the basically you can just say, okay, you solve that backwards through time. You have a discrete version. Discrete version is basically like this. This one and this one is the same. When delta t goes to infinitely small, going to very small, right? So this is the Euler's method to solving this guy. Essentially, you can say, oh, this is the continuous version. This is the discretized version. This discretized was approximately solve that. So this is our inference algorithm, right? And the continuous time is always exact. Discrete time is approximation. And when discretized delta t is sufficiently small, it goes to this. And this is basically the Euler's methods. Final y0 is the generated example. So we can certainly have a correctness of this one. For the continuous time, if you can say delta t is actually small, and then you are tracking this ODE, then you can have a continuous time correctness result, which we can say a little bit, denote this guy, right? This is the marginal PT is marginal distribution, and this is a flow, right? And solving this guy. For example, using this guy, you are reversing this guy. And let's say this guy, then basically you are saying, actually for any y hat by solving this with this formula, solving reversely backward from T1, you will have this T equals from this T, beta T. And in particular, the original is y P0, and which is basically P beta, the P data. So essentially, you say this one in the continuous time, if you have the exactly flow, it's correct. If you don't have exact flow, it's approximately correct, basically. You can also derive results like that, which will be beyond what we can do here. We just pointed this out. Essentially, you have a correctness of a continuous flow matching, and our discretization is approximation, which gets you approximate result. Okay, so this is a theory about that. The inference code is pretty simple. You have a number of steps, right? This is using the Euler methods. Right? So you learn a model using training code, which is a few lines. And the inference, you're starting with this guy yeah, basically, your T is T basically starting from okay, so this is 50 steps, or 50 by step is starting with 1, right? T is of 1 and 0.98, the next one, right? So be divided by 50, 0.98, 0.96, and so on, and up to 1. And then this is dt is this guy, it's 0.02. And then you just inference. And then that's all, right? So basically, that's the inference. Both are simple. This is Euler. And in practice, sometimes people use other methods, especially we'll talk one of the methods which used pretty frequently, which we just mentioned that. It's a so-called Hume methods. There you can say, oh, I can have high order solvers for ODE instead of Euler, because there are some other solvers. One particular solver I would just mention is this solver, right? So basically, just quickly mention, because this one you will see there are other solvers, but this one is used pretty frequently in practice. So you will just for the we are not an ODE class, right? It's just for the information only, so you know what it is, right? So this is the first one. If Euler is already done at this step. Hume actually each step has 2 evaluations instead of 1. So therefore, if you compare ODE and Euler and Hume methods, Euler's 50 steps you should compare with the 25 steps of Hume, because each of these steps you have one step, one evaluation, model evaluation. There's another model evaluation, right? So basically, you have 2 model evaluations at a different time. One is at this guy T, and the other one is T minus T delta at this particular time. And then you basically do an average of these 2 and times 2. So this is actually the method. The method makes it a little bit more accurate approximation at each step. You use 2 steps, but you have a more accurate. So in many cases, people do use these methods, but with half the step size, right? Instead of 50 steps of Euler, you use 25 steps of Hume and probably get better results. So you can do that with DDIM as well. DDIM is similar because it's also OD, but this one is easier to do because this OD is simpler. Yeah, it's a particularly simple for the flow matching. If you calculate DDIM's OD, it becomes infinity at the beginning, which we will the same. So you 2 model evaluations per step, but it's usually more accurate than Euler, so it's frequently used. I'm not saying it's always better or whatever, but when you have accurate, good store estimation, this is used quite often. So this is the method, okay? This is just for information only. So you just say this one is a higher order. I mean, you have an interpolation of these 2 fields, make it a better prediction, better tracking with this original OD. You can do classifier free for flow matching as well. It's basically the same as diffusion model, because if you think about the classifier free, right? You think about it's just change of a target for the diffusion model to flow matching. One is epsilon, one is y0. Recall the classifier free guidance is a contrast of your conditioned versus unconditioned. So conditioned and unconditioned doesn't affect y0, because y0 is never conditioned, right? Just the real image. It only affects epsilon, but both affect epsilon the same way. So essentially, you can use the same of classifier-free guidance, CFG. Conditional network and job conditioning, right, during training. And at sampling time, you combine condition on parameter. And we see the real example in our last lecture when we look at the latent diffusion models, stable diffusion. It does has observable effect of quality, right? So basically, you could do this same, but essentially it's the same. Yeah, it's the same. There's a scale. Yeah, I think we call that W last time. Maybe we'll synchronize both as S or W. Yeah. But here the guidance scale, that's all. Yeah. So basically, this is then you just use this ODE or Euler, or either you're using Euler or using this using these few methods, right? And of course, this one has more evaluations, right? If you think about Euler has one evaluation, if you have classifier free, you get two evaluations. One is conditional, one is unconditional. So you have two evaluations. If you use Hume, originally have two evaluations, now become four evaluations. But this usually is worthwhile. This kind of is far beyond what you can observe, achieve by using more steps. So basically, classifier free is something which one typically apply. Here are the experiments. The same experiment. We are not using the image. You can do this image as well, but we are not going to do that. Yeah, basically, flow matching model on the 2D. This one is the same one we did for the diffusion model. So diffusion model, we have this is the target. This is actually Y1, which is coming from standard Gaussian, right? So this is a target to standard Gaussian, is forward, backward is from standard Gaussian to these three targets. So it's a simple problem, just to test. We compiled two OD. Actually, for this problem, it really doesn't matter too much, but we would just, just provide the code. You see that. Euler, one function evaluation per step. Hume, two function evaluations per step, right? And then essentially, if I run 50 steps of this guy, I should run 25 steps of this guy. There's no CFG for this, okay? Yeah, this is all unconditional. So we match total function evaluation budgets with 10, 20, 40, 80, right? So, and for Hume, then this one is on function evaluation. For Hume, basically it should be 5 iterations, 10 iterations, 20 iterations, 40 iterations, right? Same function evaluations, different iterations. So the learned ODE transports simple Gaussian, Y1 to Y0 using flow matching. And you just compare these two methods, and then for the inference methods and so on. Here is a training. Training is very similar. You are training a flow versus diffusion model, right? You can think about that. You just change about a little bit about the target. One is predicting noise. One is predicting noise minus Y0. It's kind of noisy. We could do a little bit better than that, but roughly noisy is expected for all this diffusion model flow matching training. The reason is that there's an inherent noise. You are predicting noise, right? Predicting noise is not predictable. So therefore, it's not surprising that when you predict noise or noise minus Y0, the loss is noisy. Okay, so this one is just saying loss tends to be noisy, which is okay for diffusion model or for flow matching. Yeah, but basically, it's a random noise example. This is just typically what you see. Depends on how do you average your loss. You can see larger noise, smaller noise, but definitely, yeah, this is something. Here is what you get with our experiments, right? So basically, yeah, so basically, this is a Hume. I mean, again, this is two function evaluation. So 5 and 10 would be the fair comparison, right? So this is the fair comparison. NFE is a number of function evaluations, right? So they keep the same. I mean, so this is a simple example. So I would not say this guy is better than that. But maybe on some steps here looks a little bit cleaner than this one. Maybe, yeah, because if you have a very small step size, usually they are not doing too well. But it's hard to tell. I would say I won't say this one is just showing this one is better than that. I think it's depends on application, but at least you can try. I mean, definitely it's not worse than that. At any case, you are using half of the half of the steps, right? The same function evaluations. This one, yeah, this one maybe seems a little bit better, but you can try for other methods, other data. Some will work better, and some will probably not necessarily, right? But this is a choice, right? So summary of flow matching. The key is many times you are looking at flow matching with this scheduling. Because this is simple and effective, that's the only reason. Flow matching can be generally applied to other scheduling, but this one is the most used. Flow matching scheduling. So continuous path, this one, right? Train a network to predict the velocity, which is changed from the diffusion model. It's an epsilon minus original. So it's a difference of it's interesting, right? You think about it's a difference of your noise and original image. It's not a plus, not something, not average, whatever, right? It's a difference. And once you have that, that's the velocity. Once you have that, you solve ODE backwards. And the key of this ODE is when you do the flow matching with this scheduling, there is no blow up. It's well defined, very simple ODE. Basically, the ODE itself is just a flow field. It's just the flow itself, the velocity field itself. So that's very nice. And yeah, and so I think if you compare that, it's much simpler than diffusion model. I would say, because diffusion model, we didn't talk too much about this scheduling. We just mentioned a little bit about this scheduling, right? In the first DDPMs, we say, oh, this one is exponential, whatever. They never show that explicitly because it's you need the tweaking. Actually, if you mess up with your scheduling, you find that there's stability issues. Flow matching doesn't with this particular scheduling. So this combined with change the target prediction combined with this ODE is probably the first implementation people will take when we thinking about diffusion model. They are using. So this one makes it much easier to tune. So it cannot be underemphasized because make it much easier. Yeah. So this is a favored implementation of a diffusion model. Yeah. And to be honest, they are pretty much equivalent. If you look at the formula, they are equivalent. The only reason you don't use DDIM with a I mean DDIM is also equivalent to flow matching, ODE, right? It is because the target is different, prediction target, and this one gets you much better. Also, we mentioned a little bit about the high order ODE solver, which you can use. This just as an option. you can use Euler, and many people using this Hume. There are even higher orders. For example, 3 evaluation, 4 evaluations per step, right? Now I think people, reasonably stop at 2. Either 1 evaluation per step, which is Euler, or 2 evaluations at step, which is this method. Okay. And then that's about it. So this is all you need to know, and basically the greatly simplified diffusion model. And for practitioners, this is the first thing you should pick up if you want to implement. Okay. Yeah. So let's I think the final topic we definitely should cover quickly. Again, it's at a high level. It's about this diffusion model architecture for the transformer, right? Think about the transformer. It's a unified everything. Although now there are newer architecture being proposed, studied, but the transformer still dominates. At least in the foreseeable future. When I say foreseeable, maybe next 2 or 3 years. 5 years from now, we don't know, but certainly currently there's no real replacement, although there are candidates out there. But a transformer, you have originally coming from machine translation, encoder, decoder, right, and the text. Later move to the image, right, image classification or image representation. Now this one moves to the image generation. Yeah. So this is it's actually, I would say this is not a surprising paper at all. If you think about keeping monitor in this class and looking at the transformer, everybody would have thought about that, right? So you can think about that. But anyway, so it's done, and this paper done a careful study of that. Just like VIT, you can say, oh, VIT is not surprising at all, right? So it's a done careful study of that, making it simple. This one is also very simple, very close to the original transformer architecture, but using for the image generation instead of image understanding. Basically, you can think about the generation as a decoder, right? But this one is a noise prediction network rather than decoder. Understanding is like encoder, which is VIT, right? So these are analogous to CNN versus VIT in the encoder or discriminative classification setting. Diffusion traditionally with UNet, which is CNN, which mentioned here, we are moving that to the transformer architecture, which is far more direct. If you think about that, this idea has been there. So the latent diffusion model paper already has this transformer encoded in that, except that it's a mixture of CNN or UNet and the transformer. Here, DIT is just get rid of all the UNet components, right? Doesn't exist. Don't need those. You just have the transformer. So that's the only difference. Make it simpler. Yeah. Bring some advantages. We know uniform architecture, right? Just like VIT doesn't have any CNN components at all, right? So it's just the transformer. Here, DIT is just transformer, no CNN, no UNet. So that's all. So yeah, model size compute, and it's taking something from VIT, which is very typical, as we will see. And the global starting from status. So basically, it's a pure transformer architecture. We will see. Recall what do we do from transformer. Okay, what we can do with a transformer? Transformer process a sequence of tokens. This is for the text. You could tokenize the image. Then this gives you VIT. You have a self-attention. You feed forward the neural net. And there's some layer normalization, right? So basically, these are the 2 key components for transformer block, each one. There's no resolution reduction, just not like CNN or not like UNet, they have resolution reduction. Nothing like resolution reduction here. There's no convolution. There's no, they are all global attention, right? So this is the key. And yeah. Normalization and the residual normalization layer norm, right? Residual connections coming out, which make it's a simple. In language, tokens are the words and the subwords. basically tokenized words. Image is token image patches. For example, 16 by 16 patch, 2 by 2 patch, and so on. And the DIT is also working with image patches. They generate one patch at a time. If you think about you can serve one by one patch. If you do one by one patch, it's a pixel. If you do 2 by 2, that's typically work with the more powerful DIT, but you can do the larger batch, 8 by 8, and so on. So this is this is the image patch, and this matches what you are doing with VIT. Here is basically the latent diffusion setting. Latent diffusion, we talked about the last lecture. Basically, just say instead of looking at diffusion in the pixel space, we look at the latent space. But the latent space still image look like, right? So the typical of latent, you can think about the 32 by 32 by 4. So this is in the original latent diffusion. This coming from an image size of 256. So becomes 32 by 32 by 4, right? So this is the latent image size. You can think it's still image, but the image is in the latent. In this latent space, you encode image Y into a latent, right? You add noise, and you want to you actually want to patchify the latent into a sequence of tokens. They are so-called patchify and unpatchify, but very similar to the VIT. VIT has also patchify, right? Patchify the latent. Basically, it's a image token is a patch of p by p size, patch size. Here, because it's a generation, you have an unpatchify. So not only patchify, you will have unpatchify, and then you embed in the time and other conditioning. Right, time is you need for flow matching, you need for diffusion model. For everything, you need a time. Inject that conditioning into transformer blocks and so on, right? And run transformer blocks on the noisy latent tokens and unpatchify. So this is slightly different from the VIT. The conditioning here are different from VIT. VIT because it started with image only. There's no additional conditioning, no T, no C. So here is the components which deviates from the VIT. We will talk about that. And this one is also deviated from the standard transformer. So this one is a innovation about architecture. How do you handle that? And here unpatchify is patchify is coming from the VIT paper, right? So it's already there. Unpatchify is just the back. So it's really natural. There's nothing particularly surprising about you need this to back. So this is the architecture. Yeah. The architecture works as follows. We will talk about that. So basically, you start with this is latent diffusion transformer. If you do flow matching, the same. And in this guy, they actually, I will just quickly mention this guy. They out both noise and some additional information. It's a covariance of noise. This is a little bit more general than what we need. Actually, in most cases, you don't need this guy. You just need noise, right? You can say I can actual noise. I can also estimate, like for example, if you do VAE, right? VAE you do estimate both. You have the covariance matrix diagonal. Covariance matrix. This is you can think about the variance of your noise, but here we don't need that. So we will get rid of that. So basically only output noise. But essentially, it's noisy, noise latent, which is basically you can say it's a YT. And actually, this one there was slightly this copied from the DIT paper. This coming from this probably called the X instead of a slightly different notation. But this is a conditioning, class conditioning. Label-wise, you can use text conditioning. You can class conditioning. This is academic paper. So in the academic paper, usually people do the class conditioning for ImageNet. So this is where the label comes from. they are working with the ImageNet the data. Time t certainly should be there, right? This is where actually some most recent paper they talk about we don't need time condition and so on, but those are separate issues. But at least for our flow matching or diffusion model formula, you say okay, we need time, and this is coming to our embedding, and then DIT block is kind of like transformer block. VIT is exactly transformer block. DIT block is a little bit slightly different, is where how do you take out this conditioning. So we'll talk about this case and specifically one of that. But we'll comment on that. We will later mention a little bit more about that. Patchify is becomes image tokens. For example, one of these patchified tokens will be, say, let's just take an example, right? You have 32 by 32 by 4. So this is one of the latent standard example. Actually, yeah, this is a 32 by 32 by 4. This is coming from the 256 using the stable diffusion VAE, getting 32 by 32 by 4, right? So this is pretty standard. And let's say you have patch size of 2 by 2, right? This is 2. Then essentially it becomes 16 by 16 by 4. Each pixel is 24 by 2 by 2 by 4. Then it patchified to embed into one vector, right? Each one is a token embedding. It's one token. And so basically, how many tokens you have? You have 16 by 16 tokens. Totally is 256 tokens. So basically, you have your each image becomes 256 tokens by using 2 by 2 patches. Okay, so that's here and that's here. Then DIT block is a modified transformer block where conditioning. How to use conditioning? This is one of the innovations of this paper. And after that, you have a layer norm, you have a linear, and this is pretty standard in the transformer. It's kind of embedding, whatever, right? This one is like unpatchify and so on, and reshape and get you this. And we can get rid of this guy. We just focus on this guy. So that's the transformer. Now let's look at the DIT block. Yeah, they have several things they look at that. Because they are focusing on this class conditioning. So they have talking about this. This is one of the innovations about what they claim, right? I'll talk about this. They have additional conditioning. If maybe we can look at the other conditioning because we are not talking about it, we will talk more about this. But first, let's look at the other conditioning for this. The other conditioning, DIT block with cross attention. This one is say, oh, condition I come from multi-head cross attention, right? This one, if you have text conditioning, particularly will be helpful because you have token sequences, right? Think about in the stable diffusion, they have blip coming out with token sequences. And then your condition. This one will be useful for text conditioning, cross attention to text. For class conditioning, this is not the best way. They say this is better, right? But essentially, cross attention could be there. So this is one of the design you could get. The other one is this guy. So basically, you're just adding this condition to the sequence, right? You're just getting more tokens, basically, right? More tokens, and then you're thinking this condition matching to be the tokens, and then you're just using a standard transformer. This one is both are pretty faithful to original transformer. So if you think about these two, right? This one is pretty faithful because the original transformer does have this cross attention, right? It's basically self-attention, cross-attention. So this is a real transformer, original encoder-decoder transformer. This becomes encoder. This one is also kind of like a transformer, right? So this one is you just conditioning concatenated into our tokens, and you're adding more tokens. The token called conditioning, and then you just don't care about that. You just go through the. So this is one. For class conditioning, because this guy focused on that, they work with ImageNet. Every academics report result on ImageNet for the FID numbers and so on. And therefore, they say, this is a better one for that. So, okay, so just want to keep the context. So we'll talk a little bit about more because this one standard transformer, nothing to talk about. This one, you need something a little bit more to talk about. So we'll talk. We will soon talk about that in the next slide, but we'll already mention that, what happens, right? So this guy going through MLP, this one shared by all. And this conditioning is this guy, right? Going through MLP. And after MLP, they output these 6 numbers. In reality, this one probably just linear. When we say MLP, you could be 2 layer, could be 3 layer, but in reality, probably just one projection, linear projection. Okay, but then you go this guy, you go shift scale. We will talk more about that, and we have a shift scale, and so essentially they have actually two set of parameters. This one is one set of parameter. We will write the formula for that. This is another set of parameter. Yeah, so basically, this one is called the scale and the shift. Like batch normalization, this one actually like a scale. This scale is called the gate. Actually, maybe should really call it gate. I think later people also call the gate more instead of scale. So this is a gating function, similar to the like if you think about the LSTM or whatever, the gating. It's yeah, this one is the same. Yeah, another type. So we'll talk more about this this particular so-called ADLN0. Petrify, right? First, I mean, Petrify is pretty simple. Petrify is basically says there's noisy inputs. You are petrified to be P by P patch, right? As we give the example, it's a 32 by 32 by 4 is this one. And if this one is 2, then essentially it's a 16 by 16. So it's 256 tokens. Of course, for the transformers, because of this contention, I mean, the T is a real quadratic in T, right? Think about the attention is quadratic in T, so we want to have T as small as possible. So if I increase the patch, say from 2.5 to 4, right? And then that's a greatly reduced. It reduces much more because the T reduced by a factor of 4. So instead of if instead of 2 patch size become 4, this guy from 256 become 64, factor of 4, right? And then of course if you think about your computation is quadratic, then it's even further, right? It's becomes a factor of 4, and then because the quadratic in that, a factor of 16, you can think about that in the computation. At least in the attention layer, right? So basically, in the attention layer, at least you get. I mean, certainly in the MLP layer, it doesn't. But you can at least think about the factor of 8 to 16 is your computational saving. So any enlarge of patch make computation much more efficient. So this is an important decision. But when you increase the patch, you have a final unpetrify to be pixels becomes harder. So therefore, the good result coming from p equals 2, or even 1. But your people use p equals 2 if you look at their paper. If you are starting with a p equals 4, 8, that becomes deteriorated pretty quickly. It's a position embedding and apply to the standard transformer to this sequence, right? To this sequence. You can add position embedding for these guys. Small patch means more token and increase self-contention and so on. Okay. Unpetrify. I mean, unpetrify is pretty simple. So we will quickly talk about that. And basically, final transformer block, each token need to be decoded by a linear head into pixels, right? Each token, I don't know what the size, maybe say 256 is your embedding size, or maybe 512. Let's say 512 is your model size, right? Then you map that back to be each of these map to say if a patch size 2 is a 2 by 2 by 4, right? 2 by 2 by 4 is a 16 dimension, right? So you have a larger dimension mapped to be a lower dimension. So this is a little bit different than the let's say the text. Text usually the vocabulary category is much larger, right? You always increase your dimension when you decode. Here you are reducing your dimension. I mean, for the original paper, you have a 2C. Why 2C? Because you're thinking about both noise and variance. So you have a 2C, but in our case, we just have 1C is enough. You're reaching to the original, and then you get this. Okay, so yeah, this guy is it's a prediction, but in our case, we just P by C. Okay, so this one just describing the original 2C with both noise and variance. Here we probably only need the noise. So yeah, so basically you divide if P is 2, C equals 4, the typical number is 16. This is a number you get. Okay, so now let's look at this. So on time step and the label, right? So basically, you're thinking about the C by forming an embedding, right? This guy, yeah. Yeah, there's a position embedding which we talk about in the token, right? In the image tokens, yeah, maybe I'll rewrite a little bit, but their position embedding is elsewhere. Here, this embedding is a conditioning about both time and your. In the particular case, we are interested in they could be text, right? But the text you can use cross attention, as I mentioned. This one probably is a label. It's a label, right? Label means class label, right? So for the ImageNet. Yeah, so basically they have this embedding, yeah, they do this kind of we went through for these two guys. They are pretty authentic to the original transformer. This guy is a modification of the original transformer, so we put more attention to this guy. We already mentioned a little bit about that, but we will give the formula for the next slide. So for a class condition, this guy works best according to that, and it's cheaper than cross attention. Okay, so this is where they draw. In reality, if you think about all the current diffusion models, the real, I mean, this is academic. People report result on ImageNet, so this is important for the academic research. But for the reality, people actually really use that not for the decoding ImageNet, right? It's not class condition, it's more text condition, more like a clip style of a text condition. So this is not necessarily the best choice there. But we will talk about that for the because the other choice is pretty straightforward. Okay, so this is the conditioning, which if you are interested in working on ImageNet, and this is the default there in the DIT. DIT has open source GitHub, so you can look at their code. This is so-called MLP, but it could be a linear projection, right? So this guy is coming to say E. Remember, it's addition of your time condition plus your class condition. It's just adding them up. And then you modify this, you get this guy. And these vectors, you have a scale, shift, and the so-called gate. Yeah, gate would be the better way to say, rather than in the original, when they draw their picture, they have two scales, right? But the people call that gate. We will comment that. What is that? Scale after layer norm. Shift after layer norm. Alpha is a gate residual adding back, right? So we will see the zero. Actually, what does it mean? Zero means initial this one, so that one at the initial this guy equals zero. Yeah, not approximate equals zero, but basically initialize the final layer to be zero, or if it's just scaling. So it's not usually if you think about neural net, it's a random initialization, right? This guy says I will initialize to zero, which is better. The reason it has zero to be better is because of if you actually think about that, what happens is it have the residual, because there's a residual link, becomes identity, starting with identity map in your transformer. By not adding this, this 0 is a pure transformer architecture, right? It's better just starting with a standard transformer, the other way to say that. Here is the formula, right? If I set all this to be 0, actually this one 0 is not a standard transformer, but somehow this just say this is better. Yeah. But if this 2 is 0, it's kind of a standard transformer, but here it's just setting these guys to be 0 as well. Yeah, this multi-headed self-attention layer times this is all vectors times then plus, right? So this channel-wise time, and this is like gate because this attention is a nonlinear form, right? And multiply this guy is somewhat like a gate. So that's why some people call this gate. And this is MLP, the same MLP layer, feed forward network, which is basically this guy. So that's the roughly what it is. You know, you just see this one actually exists before, this kind of architecture. So this is not new in some sense because they exist before. Even in the UNet design, there are options like this. This is so-called film, which is in some other papers. But this guy says I set it to be 0. We didn't talk about film in this, so this looks also this one instead of film plus UNet has been appeared before, but film plus transformer, this guy's were with a 0 initialization. This guy's tried that here, right? And this one is slightly different from the standard transformer, so they say, oh, this one works well, basically. If you say the contribution about this guy, you can interpret it's not the idea actually is not invented. This kind of thing is not invented here. It's more about apply these ideas to the transformer setting. Compared with the latent diffusion paper, the transformer, they do have a transformer like a self-attention, cross-attention, right? But they also have a UNet. This guy is getting rid of UNet. And they also tried this guy in the transformer. So if you think about what this DIT is, right? So, but otherwise, you know, it's pretty standard. I want to say it's a, I want to say it's a novelty to be say that's fundamentally different you don't know before. There's nothing you don't know before, right? But it's a first successfully applied this standard transformer architecture to this image generation problem and get some good results. So that's basically how to describe this paper. Everything except this one we are not talking about that's why we talk about here. But this one is existed before. Otherwise, you know, everything is standard. Nothing really particularly non-standard. Okay, here's across the DIT architectures, what they have a scaling. This one again, of course, for when people talk about transformers, they say scale well, right? That's something, and this is shown. And you can see there's small transformer, base transformer, large transformer, XL, extra large transformer. And these are the standard architecture which is exists in the GitHub. So you could just download that, just using that yourself. And the patch is 8. 8, of course, is much simpler because you have a smaller number of tokens, image tokens, and these are up to 2. So these are the, and then you draw and computing the computation, and here is where you get with the largest XL2 is the one which is offered by that paper, offered by that GitHub, is the configuration. Get the largest and you see get best result. FID is the smaller the better. This is on ImageNet, and basically, yeah, basically that's about it. And the model family, you have these guys, right? And this number of parameters, patch size, right? So this is basically what it is. And they show a nice job. And there are many other papers, many other things which mentioned in that paper, which comparison. There are a lot of studies. So the paper actually is more about a study of a transformer architecture rather than inventing something real new. In summary, DDIM can be written from a general interpolants, right? And then there's the key is this guy. So this is what you should, if you think about the implement diffusion model, this is basically what you should use. And these guys and the diffusion transformers, you have a UNet and you have a and then that's all. Yeah. So basically, these are the two papers which matter. And this one is a follow-up of this paper talking about the flow matching. This one is a diffusion. And this one basically doesn't, it's just additional ablation studies. That's all. Yeah, this one is okay. So that's all. Yeah, thank you. And so we are done. And hopefully, yeah, this covers all the basics. If you are hopefully can be helpful either in research or future work and so on. This give you the general ideas about all the different models, the common models, how they work. Okay, thank you. Okay, bye.